So the main topic for this week is dyadic data. So dyadic data is a special type of cluster data structure in which each cluster has exactly 2 time points. And there are several common examples of this, such as monogamous couples, roommate pairs, doctor-patient relationships, and more. And while our sort of general HLM methods apply to many of these examples, there are some really subtle complexities in dyadic designs that need to be addressed. So the first thing is that in dyadic designs, you'll actually often see variables separated out into 3 different types, and 2 of these correspond to what we're used to, and then there's one sort of new one. So between variables are like level 2 variables, so they are only they only apply to the actual cluster of the dyad. Mixed variables have variability at both level 1 and level 2, and so those are the same as our normal level 1 variables. And then there's a new type of variable called within. And so this is sort of like a centered within cluster level 1 variable, and then it has no level 2 variability. We actually saw an example of this when we were looking at longitudinal designs last week. If you recall, we were looking at a balanced longitudinal design where every person in the design was measured at the exact same number of time points. So time was a strictly within variable because it had no level 2 variability. Each person was measured at week 1, 2, 3, and 4, so the average time for each person was exactly the same. So another example in dyadic data might be something like if you are looking at pairs of tennis players. So if you look at a bunch of tennis games, in each one-on-one tennis game, one player serves, so there's variability within the dyads because one player serves and one player does not. But this is consistent for all dyads, so there is no between dyad variation. Each dyad has one server and one receiver. Another important idea in dyadic data is distinguishability, and there's 2 types of distinguishability. There's conceptual and empirical distinguishability. So conceptual distinguishability means there's some variable, essentially, that is either within dyad or mixed. So essentially, there's some way of identifying one of the members of the dyad as compared to the other across all dyads. So in the tennis example, being a server would be an example of a distinguishing variable because you can distinguish for each dyad one player is the server and one player is not. A distinguishing variable could also be mixed. It could be something like age, where you say each dyad has one person who's older and one person who's younger. So that is conceptual distinguishability. And conceptual distinguishability is necessary, but not necessarily sufficient for empirical distinguishability. So with empirical distinguishability, you also need to be able to use the variable to meaningfully distinguish the 2 members of the dyad on the outcome. So in the tennis example, you would need to be able to say that whether someone is the server or not. Let's say you're measuring who's more likely to win. You need to say the person does being the server make someone more or less likely to win. If being the server doesn't make someone more or less likely to win, we would say that being the server is an exchangeable variable. So when variable is conceptually distinguishing but not empirically distinguishing, we call that exchangeability. And we'll look at an example of this as well. So standard designs, we can use, for the most part, often we can just use regular HLM techniques, though at the very end of this video, we're going to talk about an exception to this. The key difference is that we can't have random slopes. Why can't we have random slopes in standard designs? The reason is because we only have 2 observations per cluster, and that would mean that we have a slope and an intercept parameter for every cluster, and so we would have 1 parameter for every observation, and the model wouldn't be identifiable. And this is similar to what we saw last week when we were trying to add random slopes for different variables in the growth curve model, where eventually we wound up with more parameters than observations, and that's not an identifiable model. So here is an example. Here we're looking at college roommates adjustment based on their amount of drinking and their campus of residence. I mean, we could think of this as being Rose Hill and Lincoln Center as the campus of residence. And note that we have only random intercepts here, but otherwise this is just a pretty typical HLM model. And here's the output. Again, nothing too new. We have our fixed effects, we have our random effects, all pretty standard stuff. So interesting twist in dyadic data is that instead of a contextual effects, the way we have learned about them so far, we can actually have what's called the actor-partner model, which is a slight twist. So in normal HLM, when we have many observations per cluster, we use the cluster mean as to represent contextual effects because we need some representation of the entire cluster. But when we have only 2 observations per cluster, we actually don't need to take the mean. We can just look at both the focal person and their partner's value on the variable, and that winds up doing the same thing. Since the average is implied, since you have both observations, we don't do this with larger clusters because that would mean having many parameters for each member of the cluster. But here we only have 2 members of the cluster, so adding the partner's value only adds 1 extra parameter, so it winds up being the same as just adding the contextual effects. And this is called an actor-partner model, and it's also a little bit more interpretable in some ways in the sense that you wind up using both the actor's predictor and the partner's predictor to predict the actor's outcome. So here's an example of an actor-partner model where you have the actor's drinking level and their roommate's drinking level, as well as campus. And again, pretty standard output, fixed effects, random effects, nothing too new here. In distinguishable designs, the most straightforward way to fit these models is to simply include a dummy variable for the distinguishing variable. So in this example, we assume that roommates are paired between domestic and international students. So every pair of roommates is 1 domestic and 1 international student. And then we include a dummy variable to indicate each roommate's status. And we, once again, just have this extra dummy variable of citizen, and we get the same familiar output. We can test exchangeability. In this case, we only have 1 variable to distinguish the roommates, which is the I put the wrong output here, which would be citizen. So this is not the correct output. There should be 1 extra line here for citizen, but we could look at the significance of the citizen variable to determine whether it was significant or not. But sometimes you'll have more than 1 variable that tests for distinguishability, in which case you could do a likelihood ratio test using 1 model that has all the distinguishing variables, and then 1 model that doesn't have the distinguishing variables. And this is a way to test, again, empirical distinguishability or exchangeability. So here in this case, we note that the model that has the distinguishing variable is not significantly better than the model that does not have it. So we would say that citizen is an exchangeable variable in this setup. We can also do overtime designs. So in overtime designs, you're essentially doing a hybrid dyadic and growth curve model. And so one thing to note is that when both partners of the dyad are measured at the same time, we have what we can treat the time and person as crossed rather than nested. However, if they were both partners were not measured at the same time, which is unusual, you don't see many designs where both partners are not both measured at the same time, then we could not treat time and person as crossed and nested, and we would have to treat time as also nested within person, which was nested within dyad, and then we'd have a 3-level HLM. Note that we also have more than 2 observations per dyad now, so we can include random slopes. We'll typically start with time, and then we can consider other random slopes at that point too, but time is really the one we want to focus on. But all the other things we talked about in terms of distinguishability and actor-partner models apply here. So in this example, we're going to look at marriage satisfaction in heterosexual couples over time, and we're going to allow time to interact with our distinguishing variable, which is wife. Since these are heterosexual couples, each model has a husband and a wife. So we're going to see if time interacts with our distinguishing variable to see if the effect of time is different for the different type of partner. And so here we see the interaction is not significant. T is it's below 1.96. And I included the random slopes for time. But again, otherwise this output is pretty familiar. And as is this output, once again, random effects. And because we have the random slope now for time, we also have the correlation between the intercept and the time variable. You can also include the residual covariances over time or heterogeneous variances over time, but for that, as we discussed, you need to use an LME. So there's one last thing that we need to talk about, and this addresses something that's discussed early on in the reading for the week, and this is a hidden assumption in HLM that is often treated as so trivial that it's not even really discussed. And this assumption is that observations that are within the same cluster are not just going to be correlated, but they're going to be positively correlated. So when we do HLM, what we're doing is we're modeling cluster-specific relationships by specifying variance across cluster-specific intercepts. So we're saying if there was no cluster-based correlation, every cluster would have the same intercept. But because the clusters have different intercepts, we're saying that there's some unique variance that's attributable to these clusters. And essentially, this implication is that the variance within each cluster is positive. There's a positive correlation within each cluster because variance can only be positive. However, this is a perfectly reasonable assumption in most HLM cases. We almost always expect the correlations within a cluster to be positive and not negative. But this isn't always the case. There are some rare cases in other HLM and some slightly more common cases in dyadic data in particular, where you actually expect correlations within clusters to be negative. And this is usually something that you can infer based on your design. This isn't something that you expect to just happen randomly. So this is something that is usually baked into your design. And so examples would be compensatory or competitive situations or situations involving social comparisons. One example that just pops into my mind is if you have a bunch of people playing one-on-one games with each other. So I think dyadic data analysis will apply to game theoretic situations a lot. So let's say you have two people playing a zero-sum game. So the higher one person's score is, by definition, the lower the other person's score is. So in this case, by definition, within each dyad, the correlation has to be negative. The higher one person's score gets, the lower the other person's score gets, and the lower the one person's score gets, the higher the other person's score gets. So this presents a problem. And if you read the Kenny and Kashi paper very carefully, you notice that although they describe multi-level modeling methods, they actually don't use HLM methods as we typically do. And this was one of the things that Dr. Chen was noticing, in that they weren't using the random command in some of their syntax, and it was a little hard to figure out what they were doing, but they weren't actually using HLM the way we've learned it. They were using a repeated measures technique, and HLM is a type of repeated measures technique that's become popular because it produces very interpretable parameters and it's computationally flexible. But Kenny and Kashi suggested that we don't use HLM for dyadic data specifically for this reason, because it makes it impossible to capture potential negative within cluster correlations. And so they use something else called compound symmetry to account for the cluster correlations. And so this is an alternative technique that can be applied, and actually in cases where the within cluster correlations are positive, in some cases it produces an equivalent model to the HLM models that we've looked at, but it's parameterized a little bit differently. The issue is that from the perspective of dyadic data analysis, this is all super sensible. We should use this alternative compound symmetry approach, but dyadic data analysis is a somewhat kind of niche methodological area, and the sort of pre-packaged programming solutions that have been developed don't really fit this approach super well. And especially, this is definitely true for LME4. NLME does offer some options for this, and SPSS and SAS also offer some options for this, but the programming isn't nearly as straightforward as we like it to be for a lot of the work that we do. So one place we can look is in NLME has this function GLS, which is generalized least squares, and we'll look a little bit at how we can use this for dyadic data in the standard model, which would have allowed for within dyad correlations to be negative, and we can show how this, in this case, the within dyad correlations are positive, and how this is equivalent to the HLM models that we fit as well. So GLS is similar to LME. The only difference is that you can only specify grouping variables in the correlation structure. So what you're essentially saying is that there are different within group correlations, and we're using this approach called compound symmetry, which you talked a little bit about in lecture, and I think Dr. Chan will probably clarify a little bit more in lecture next week. So we call this with this core comp sim item under the correlation argument. So this is saying there's compound symmetry by dyad, and remember in NLME functions we have to call the NA omit to specify what to do with missing data. And when we view the output, we get a row parameter. So this is similar to what we saw with the AR1, the autoregressive lag one. It's the same parameterization where we have row, but this, instead of representing the correlation over time, this now represents the correlation or the compound symmetry by group. So we only have 2 observations per group. So we have the diagonal, which has the variances, which are assumed to be equal, unless you specify a method that doesn't fix them as equal. And then we have one off-diagonal element. It's a two group. Each group has 2 people, so it's a 2 by 2 matrix. So there's one off-diagonal element, which is the correlation, and that is how we parameterize the within cluster correlations. So here you see what I call a summary and get the row parameter. So note that the row parameter here is 0.62. And here are the fixed effects for this output. So we get fixed effects very similarly as to what we would in HLM. But note that we don't get random effects. I mean, you can't see it here because it's cut off, but we don't get random effects. This row is replacing our random effects in this case. And I'll demonstrate how this is equivalent to the random intercepts formulation. So row is 0.62. So this is also, it was cut off in those slides, but there was another at the very bottom. It noted that the residual standard error is 1.552. So this is sigma E. This looks like the matrix that we were looking at in when we were looking at growth curve models. So essentially, this means that the residual variance in this model is 1.552 squared is 2.41. And so we get the residual covariance. This is the off-diagonal element that we're interested in by multiplying the residual variance by the row parameter. And so we multiply 2.41 times 0.62, and we get 1.49. So let's see what happens when we fit this exact same model using HLM instead of compound symmetry approach. So here I use the LME from NLME, so just to keep the package consistent. And note, this is our intercept variance. It is equivalent to this sigma squared E times rho. So what we're saying here is essentially the off-diagonal element in this compound symmetry approach is equivalent to the random intercepts. Note that this is only true when rho is positive. The advantage of this approach using GLS is that it allows rho to potentially be negative, which the HLM approach does not. Also note that the fixed effects are all exactly the same. You can see here they are pretty much the same. The only difference is slight little differences in the algorithm, but the fixed effects are identical. So the advantage of the GLS approach is that it allows rho to be negative, which HLM can't accommodate. The reason we don't use GLS is that it is a bit less flexible in more complicated grouping structures, especially in cases where the clusters have many observations, and it is much more difficult to think about things like random slopes. It's not impossible, but I have not figured out how to program that correctly. Again, it's likely possible, and there are some examples in the paper that show how to do it in SPSS and SAS, but it's a bit beyond what we're able to teach here because this really isn't technically an HLM approach. It's a different computational approach that would require quite a bit more foundation than what we've offered you.